How are we doing today?
Well,
Yeah. Okay.
Yeah.
Generally blasé. Okay. So, are we ready? Did you bring enough for everyone, Victor?
we can all share.
You can slice it in infinite slices.
So, we're going to continue to march on. We have been making good progress. How's the homework going? Well, you had 2 weeks, though.
Yeah,
we didn't finish chapter 5 until last minute.
Well, I was waiting till the last minute.
That's why I could give you the entire term, or I could give you 3 days. It's like there's no difference.
First due, first served.
Yeah, I have actually had professors who have had no homework due all semester, or professors who have had everything is due at the end. Like you don't have any due dates all semester until the very end, and then you have to turn everything in.
It's gonna make all they're gonna put us off.
It's
I usually do like 1 or 2.
it puts a lot of responsibility on you guys for managing your time well, and I haven't found that everyone responds well to that.
This was a good teaching lesson
So,
in this instance.
yeah. Well, I hope that the homework is helpful for you. I think it will be.
I think it is.
So, did you bring enough for everyone, Jordan?
I'm the one that.
Yeah, he's sharing.
He's sharing.
I didn't get my piece.
We didn't help you. We didn't help you buy that. I mean, everyone had equal opportunity to ask Victor for a piece, so. Oh,
That's a good point.
So
I didn't hear
it's not
you
my fault that you
guys.
didn't
I
take
thought
advantage
he was
of
just-
that.
I didn't hear you guys. I thought he was just-
Yes, question, Alex.
Yeah, so, where it was drawing the contours that says that to intersect one passive, I forgot how the phrase in notes is, like one passive element. How are we supposed to determine what is a passive element?
Okay. So there are active elements, which are sources,
Okay.
and there are passive elements, which are things that are not sources.
Okay.
Elements that are not sources.
So, like a capacitor,
That's passive.
That would be considered passive, even though it can act as a.
So-
as the power's flowing through the system, it's a passive element. But if you disconnect the power, then it becomes a active element.
So
Right?
I think that the confusion here is that you're thinking it can store energy, so it can supply energy to the circuit, right? So how do we say if it's active or passive? And the meaning of active versus passive is that active has external power being supplied to the circuit.
Gotcha. Okay.
So it's an input to the system from outside. And a passive element is one that gets its energy from inside the circuit. It can store it for a while, it can release it back, which is fine, but it just doesn't get its energy from outside. So that's why source elements are the only active elements that we consider. Soon we'll be talking about op amps, operational amplifiers, and those are also active elements as well. They have external power that comes in through them, so we'll talk a little bit more about those very soon. And that's actually what we're introducing now, transducer elements, okay? And that's what an op amp is. So to give away the punchline, it's not the only type of, no, it's cool, you know. It's not like I built the entire semester up just for this big reveal and it just went away, but you know, there's always next year.
A good student would get there on their own, right?
Could still what?
A good student would get there before you.
That's right. That's right. It just shows that you guys, I'm only impeding your progress in this class. That is my role, to slow you down.
That was the plan.
Yeah, but you have to be really good sound.
Okay. I just like to listen. All right, okay. So ideal transformers and gyrators are what we're going to talk about today. So we've been talking about one-port system elements up to this point, right? One port means that there are two terminals that connect to the system. Okay, so that's what we've been considering, those types of elements. Now we're going to learn about a new type of element. Two-port system elements can be used to model transducers. So there's this physical idea of transducer elements that we're going to talk about, and they're modeled by two-port system elements in our linear graphs. Okay, so transducers are elements that transfer energy between two energy domains and within a single energy domain. So it can go between two energy domains, or it can be within a single energy domain. So you can go from electronic to electronic. You can also go from electronic to mechanical, or mechanical to electronic. So we are going to use these to be able to model things like motors that go from electrical to mechanical, or generators that go from mechanical to electrical. Okay, this is where the mechatronics, they get glued together now, right? So we are now at the hyphen, even though we kind of suppress the hyphen when we write mechatronics. But we could write mecha-tronics, and then we would be at the hyphen. We are now at the point where we glued the two words together. We're at the joint. The interface? I don't know. I'll have to think about that. So anyways, each port, so we have two ports on one of these two-port transducer elements. So this is a little diagram that we could draw. Each port, so here's one port over here, and here's another port over here. Each port has a through and an across variable. Okay, so this port has an across variable and a through variable. This port has an across variable and a through variable. We require that the power into each port be positive. That's our convention. Okay, if we do that, we can write that due to conservation of energy, we're going to say we don't lose any energy in here. Now, that is an assumption that we're going to make that is not always valid. So we have to be able to come back to this point and say, maybe there's a certain efficiency. Maybe power 2 is like 97% of power 1. Okay, so if that was true, if we had 97% efficiency transducer element, we had to come back here and put in 0.97 before the P2, right? And then we could do the rest of this derivation. For this derivation, though, we're going to assume that we conserve power, we conserve energy, and there's none lost in the transducer element. A lot of transducer elements are pretty conservative. They don't lose a lot of energy, so we will make that assumption for the first pass at this. So if you add them up, they have to equal 0. And of course we know by definition that the power into each of these ports has to be the through variable multiplied by the across variable. So these are the generalized through and across variables that we have seen before. And we're going to then solve this, so we can rearrange this to find relationships between the ratio of across variables to the ratio of through variables. We're going to define that this is going to be the transformer ratio, TF. This is one symbol. It's going to define one quantity. We use two letters to define one quantity. It's kind of unusual notation, but that's what the book uses, so that's why I use it. So transformer ratio is the across variable ratio, which is also equal to, based on this equation right here, negative F2 over F1. Okay? So you can solve this for V1 over V2 by subtracting this term over, dividing both sides by V2, and dividing both sides by F1, and you get this relationship here. And we can also define the gyrator ratio, which is the ratio of V1 to F2, which is also equal to negative, based on this equation, negative V2 over F1. Now, we call TF the transformer ratio and GY the gyrator modulus. Okay, sometimes we forget and call it a ratio. In order for the above to hold, one of the following equations must hold. Okay, one of the following equations must be true. Either V1 is equal to TF V2 and F1 is equal to negative 1 over TF F2, or V1 is equal to gyrator modulus times F2, and F1 is equal to negative 1 over the gyrator modulus times F2, times V2. And that is when we have a specific two-port element or a transducer element, then we know that one of these two formulas must hold, assuming it's an ideal one. It's either going to be this relationship that holds, or it's going to be this relationship that holds. And determining which of these relationships hold for a specific transducer is how we determine if it's a transformer or a gyrator. Okay, so yes?
I'm a little confused. I see that TF and GY appear to be algebraically identical.
They're not. So notice that this diagonal is the opposite diagonal. So this one says that V1 is equal to TF V2. This one says that V1 is equal to GY F2. So notice that in this case, the across variables directly relate from one side to the other, right? So for a transformer, the across variable on one side is directly related to the across variable on the other side. Whereas for a gyrator, the across variable on one side is equal to is directly proportional to the through variable on the other side. So the gyrator sort of crosses them, and the transformer relates them directly.
Okay. I was thinking about the equations directly above those systems.
So these equations, they're both. So what I'm doing is I'm defining the transformer ratio and the gyrator modulus in these, and I'm just saying I'm defining gyrator modulus to be this ratio, and defining the transformer ratio. That's why I use this definition symbol to be the cross variable ratio. And the second equality here is just the implication of the conservation equation above.
Okay.
So that equation above says, oh, this ratio is also equal to this other thing. Here. Okay.
Okay, now it makes sense.
Cool. So yeah, so essentially we have two possibilities. Either the across variables are directly related, or the across variable is So we'll start over. Either the across variables are directly related and the through variables are directly related, or the across variable on one side is related to the through variable, and the through variable is related to the across variable. So those are the possibilities. You want to have one or the other. So if the former holds for a transducer, we call it a transformer. So when the transformer ratio relationship is the one that holds, we say it's a transformer. If this other equation holds, the latter one with the gyrator modulus holds, we call it a gyrator. So those are the two possibilities. And so when we encounter a transducer element, we don't know if it's going to be a transformer or a gyrator until we discover how the across variable, the across and through variables on one side relate to the across and through variables on the other side. Okay, so that's what we need to know to determine if it's a transformer or a gyrator. So use the following steps to determine the transformer ratio for a given transformer. Gyrators are similar, okay, so we can use a very similar procedure. So we can start by establishing positive V1, F1, V2, and F2 on a diagram, okay? Then we determine the relationship between V1 and V2, okay? Then we define the transformer ratio to be whatever that ratio is, V1 over V2. So we solve that, from this relationship we can solve for V1 over V2. That defines what the transformer ratio is. And then, finally, we can define the F1, F2 relationship with negative F2 over F1 being equal to the transformer ratio, and then that defines a separate equation. So we don't have to start with the cross variables. We could start with the through variables and define what TF is from the F1, F2 relationship, and then work it backwards, right? So all we need to know is how the cross variable on one side relates to the cross variable on the other side, or the through variable on one side relates to the through variable on the other side. Either one of those relationships will define the transformer ratio for us. And then we're off to the races, okay? So a number of transformers and gyrators are analyzed in the textbook in Chapter 6. The table right summarizes the results. So there are a bunch of transformers that are described, and there are just a couple of gyrators. There are a lot more gyrators and transducers. The reason the book lists these is not to have an exhaustive list, okay? It's just to show you how to do the analysis so you can come up with the transformer ratio or the gyrator modulus on your own and do the analysis. So it gives you sort of a feel. So does everybody know what a rack and pinion is? Okay, maybe a few of you know. So a rack and pinion is what you have if you have a gear. And you know gears, they've got teeth on them, right? I just didn't draw all the teeth. So there's a gear, and then there is another gear that has an infinite radius. This is the rack side of it, and it has teeth as well, and they engage with the gear, and so you get to change rotational motion, exchange rotational motion for translational motion, or vice versa, right? You could change linear motion, translational motion into angular motion. So that is a rack and pinion. It is, so if you were to write, so here's like a little sidebar. If you were to write the relationship between one side's kinematics and the other side's kinematics, you would say, okay, well, the most immediately obvious relationship, to me at least, and it might not be obvious to everyone, but is that we can exchange the angular velocity of this gear and the linear velocity of this pinion, or rack, is they're related by the radius of the gear, right? So we would write that the linear velocity v is going to be equal to r theta dot, right? And where theta is the angle of the pinion. Yeah? Does that make sense? And so we've got this relationship, and notice what we're relating here. So theta dot is, we would often just use omega, right? So this is the relationship. It's just like when something's rolling, right? Same. So that that is a relationship between an across variable velocity and an across variable angular velocity. Yeah.
And so you're relating the angular velocity of one of the teeth that's hit on the pinion that's hitting the velocity of the rack. So like when they both touch, is that what you're relating?
I'm relating the velocity of this. So let's say this is a fixed pin. Okay. That's a fixed pin. I should have drawn this larger, obviously. It's a fixed pin. It's rotating. This rack is on bearings or something, and it can move back and forth. Okay. So let's say that has velocity of v. The rack has velocity v, and this has angular velocity omega, and the gyro also has radius r. So the velocity here is going to be r times omega. Does that make sense? So v is an across variable, omega is an across variable. So what kind of transducer is this? Is it a transformer or a gyrator? It's a transformer, because it's across is related directly to across. Now, there's also a relationship between torque and force here, but that wasn't the way that we went about finding the relationship. But we know based on the fact that, if our transformer ratio here is going to be R, so we go up here and we say, oh look, transformer ratio is R, so we'll just say this is TF, then that means that the force has to be equal to negative 1 over R, and I'll put parentheses to make it clear, 1 over R times the torque. So we know that relationship must hold as well. Yeah. So that's kind of nice. So we only need one of them. We could have started with the force-torque relationship. We would have discovered that to be true if we would have done a dynamics analysis instead of kinematics analysis. But the relationship, you can use either one to define what the transformer ratio is. Okay, so there's rack and pinion. There's a little miniature example I did. There's a gear train, so the number of teeth in a gear, or so ratio of the number of teeth in a gear or the ratio of the radii of the gear. That's another transformer. A DC motor, we're going to learn in just a moment. This is a transformer. We're going to do an example of a DC motor. A slider crank. You guys know that mechanism? So a slider crank looks like, just make sure I'm not going to use this space for anything else. A slider crank looks like if you've got, say, a motor rotating a flywheel. It didn't really need to be a flywheel, but we'll just make it a flywheel. And this is this is a pin, and it's maybe being rotated. We could pin a linkage, and then on this part we could have a rail or something. Whoa. We could have a rail that it's sliding on. So you can trade rotational motion for translational motion as well. So yeah, so lots of different types of linkages. I really want to do a class on dynamics of machines so you guys can become more familiar with these types of linkages. They're pretty cool. You can do all kinds of cool stuff with them. Block and tackle, you guys saw that in dynamics a lot, I think, with the pulley system. Levers, belt drives as well. So they're kind of like gears, right? Electrical transformers as well. So electrical transformers, we've already talked about those, right? and they take a voltage and current on one side of the circuit and trade it for a different voltage and different current on the other side of the circuit, right? That doesn't change energy domains, obviously. And there's also a fluid transformer, which we won't talk about in this class. Hydraulic ram is another example. So if you have a piston and a cylinder, so your piston can relate the pressure on one side, which is actually a cross variable, to a force on the other side, which is a through variable. So we aren't talking about fluid systems in this class, but that's one thing that we'll talk about in system dynamics is a piston cylinder system, and a displacement pump is another example of a gyrator. There are others as well, but these are just some that I noticed the book had, and I just listed them here. And it says which page of the book they're found on, so for what it's worth. Okay, so a DC motor is a great example of a two-port element. So here is a system that has the motor connected to a load. We're driving that motor with a voltage source, okay? So we want to draw a linear graph, and we want to know what are the two elemental equations for the two-port motor element. Just like with the transformer, we have two elemental equations for two-port elements, okay? So where our typical one-port elements only have one elemental equation, our two-port elements have two. Maybe not surprisingly. So this is, by the way, this is our model for a motor. We have an electronic connection to it, and the windings, so for a DC motor, the windings are going to have a resistance to them and also an inductance to them. And then they're, of course, going to then interact with the mechanical side as well. So the load on the other side is going to affect the electrical aspects. Yeah?
Could the commutator on a DC motor be thought of as a capacitor? Or is that just...
No, it's not typically thought of as a capacitor, no. So the commutator, I don't know, I might be able to... I think I'm in the lab, I'm going to do a little bit longer discussion of DC motors.
Okay.
But it's there to allow you to have the electrical contact switch.
Yeah, I understand how it works.
Yeah, it's there's typically not considered to be a capacitance in DC motors. That being said, there might be a little bit, but it's usually negligible. Yeah, so we usually ignore it. And the inductance is typically small as well, as is the resistance, but they're important enough that we do include them in most models. We don't always. Sometimes you can get away with it, but usually we do. So you may hear one day about back EMF and I'll talk a little bit more about that in the lab too. But back EMF is what people call the effect of this motor back on the circuit, okay? And there's endless confusion about that, okay? Confusion need not arise, though, if we recognize that this electronic circuit here is going to interact with the mechanical dynamics through these two elemental equations that we're going to describe this element with. And that's all we need to worry about. We don't need to worry about, so you're taking into account back EMF when we do that.
Okay.
So let's go ahead and draw a linear graph first. So one of the things that's interesting about a system, notice this is an electromechanical system, right? So we're doing mechatronics, finally. Wow. Yes. Rage phase. All right, so we need to have two different grounds in our linear graph because one is the electronic ground, the other is going to be the mechanical ground. So the mechanical rotational system has a reference velocity. So let's say our reference velocity, we often choose it to be 0. And our voltage is, by definition, always, at reference is always 0. Okay.
Is that velocity or voltage?
Sorry, voltage. Did I say velocity?
No.
You did
Oh.
resist.
I was just curious.
You're just trying to mess with me, huh? So this is voltage. So when you end up with a system that is electromechanical and it's translational mechanical system, then confusion sometimes arises. But just be cautious. Try to change the V on one to something different. There's one alternative symbol for voltage that is common, and it's E. E is also common. So you could use E.
Lowercase e?
Either one, lower or upper.
Usually lower.
Yeah.
But then what do we use for this number?
You don't. You just stay away. I don't know. I mean, you just have to know the context for each symbol.
So if this was moving, then we could do.
Yes.
Okay. Good to know.
So we have our grounds. On the electronic system, how many nodes do we have?
2, 4, 3, it looks like.
So this is going to be our ground. Okay, so we're going to connect ground as we often do to the negative terminal of the source. So that'll be our ground associated with this. And there's one node, 2 nodes, 3 other nodes, right? So 3 plus ground. So we've got 1, 2, 3. And then the mechanical system has how many distinct angular velocities? Just one, right? The flywheel and the shaft are all at the same angular velocity. Besides the ground, which this bearing is connected to. So we only have one node on the, other than ground on the mechanical side. So the electronic side of this is easy enough to draw in. The voltage source, Vs, and we have it dropping towards ground, right? So we can draw it towards ground. And we have a resistor that comes up next, right? And we'll do our typical away from sources towards ground arrow direction. Then our inductor is next, right? And then we go through the motor, right? And so the linear graph that we draw is like this, okay? Where we have an element that references our ground on this side, but is going to interact with this other one, okay? This is how we draw it on the linear graph. We always draw these towards ground. That's the kind of convention that we have. And on the rotational side, we have our moment of inertia, which always goes to ground, right? We have our bearing damping, which is going to go to ground because our bearing is connected to ground, which they usually are, right? So this is J, B. And then we have the interaction with the electrical side, right? Which is drawn like this. And so we call The side that has the source on it that's driving the other side, we usually label with a 1. And the side that's receiving the energy from the source is usually side 2. Okay. So that's just a convention for labeling them. You don't have to use those. Yeah.
So, quick reminder. So, is the resistor and the inductor, are they going those directions because that's the loop we chose?
So we should have drawn in our direction of assumed voltage drop. We often choose those to go towards ground and away from sources, right? We should have done that, though. That's a good point. We should have made that assumption. Okay. Now, we've got our linear graph, and we're going to learn how to construct a normal tree from that, but not in this specific lesson. It's in the next set of notes. But for now, we can. I already said that this is going to be a transformer because it showed up in the transformer section up here. And on linear graphs, we draw in a box on transformers. And we often will label that box with whatever the transformer ratio is. This is because we haven't found it yet, right? So we could just say like TF. Now, let's figure out what the relationship is between side 1 and side 2 of the motor. Okay. So the through variables are related. So for the motor, I should have probably said that, right? For the motor, the relationship is, and this is something that you would probably have to look up, right? Like you don't necessarily know off the top of your head what the relationship between the torque on one side, how it's related to the current on the other side, but it happens to be related by this relationship. -2R N, I'll define these symbols, B L times I1. Now, yeah, you may have seen this before at some point.
Looks like it has something to do with solenoid.
So this is the rotor radius. Have you guys seen motors in detail before?
And taken apart.
So this is part of why we have a motors lab now, so you guys get more familiar with them. But we'll go through a little bit of theory when I do the lab. It's the last lab of the year, an ME316. And I'll go through in detail some of the theory behind motors. And there's some really cool videos that show like how current's flowing. And yeah, we'll do that. N is the number of coil turns. So there are DC motors that have windings on both sides. So you have an interacting magnetic field that's helping to drive the motor, and you have an electromagnet on at least one side. The other side can be permanent magnets, or it can be electromagnet as well. It just depends on how it's set up. Different types of DC motors. So lots of good stuff. We'll learn more about it. B is the background magnetic field. And L, if I can kind of squeeze it in, is the rotor length. Now, this is an equation that is roughly true. So you could come up with what we are about to define, which is going to be the transformer ratio for this motor. What we'll often do is not use this theory. We'll build a motor, or the manufacturer will design and build a motor, and then they'll test to see what is the relationship between the current on one side and torque on the other side, and then they'll give you your transformer ratio. But they give it to you as a set of notes in I think 2 sets of notes, maybe 42. We'll explain in the most confusing way that you could conceive of. Okay, it's horrible. So we'll review how to interpret these constants that they give you. They're called motor constants. They give them to you in the most confusing way you can imagine, and we will see, and we will laugh at that. So, therefore, our transformer ratio. Notice if we go back up here, we have the through variable on side 2 is related to the through variable on side 1, right? So we go back up here. Aha! We have a ratio of through variables, so we can look up what the transformer ratio is from that. So F2 over F1 is the same as T2 in our case over I1, right? And if we take the negative of that, we have the transformer ratio. So we can divide I1 over and multiply both sides by -1. And what's left over here is our transformer ratio, which in this case is just 2RNBL, and that's it. And we can write our 2 elemental equations. V1, I1 are the one side, and on the other side we have a matrix times omega 2 times T2. So this is the across variable and the through variable on side 2. This is the across variable and through variable on side 1. And we need to, we know that the across variable has to be directly related to the across variable by TF, right? So from back up here, this describes the 2 elemental equations for all of these things. So since we knew it's a transformer, so we found out it's a transformer, all we needed to define was what TF was, and we know we can just write this. So I'm just going to write that same exact thing over again. 0, 0, -1 over TF.
This won't apply. Will this apply most of the time? Or?
This applies every time. So whenever you have a transformer, this is going to be this is going to define the 2 elemental equations. So this defines 2 equations, right? The first equation, scalar equation, is V1 equals TF omega 2, right? That's one of the elemental equations. The other elemental equation is I1 equals -1 over TF times T2, right? So, or it's 2 scalar equations. Okay? How does that feel? Pretty cool, yeah. Vaguely acceptable. Yeah. Awesome. Well, I think we'll just go ahead and call that good for this lecture then.